So to start off, we are going to start off with the first topic, which is the review of scalars and vector products, scalar and vector triple products, and scalar and vector products for four vectors. So for scalars, we are not gonna go that deep into scalars because this is about vector calculus, and we are not going to talk about scalars that much in this place. So, but before that, let's talk about what is scalar. I'm not gonna write the definition because it's not that important for this course, but I'm gonna tell you. Scalar is anything that has a magnitude, and direction is not important for it. Okay, so that's it. So, for example, if we say a mass, suppose something is 1 kg. If something is 1 kg, we don't need the direction 1 kg east, 1 kg north. That does not make sense because 1 kg is sufficient to describe it. So that would be a scalar. So now, starting with our first topic, we are going to start with vector. So let's write this. Mm, Vector. So what is vector? So that's the first thing we need to answer. So vector is basically a physical quantity. So what is a physical quantity? It's basically anything that can be described. So physical quantity with magnitude. So magnitude means a number, and direction. Direction meaning where it is going, and defined sense. So this defined sense is a term that you might be hearing for the first time. If you know about vectors, this might not be something that you might have heard. So before going into what is defined sense, let's just talk about a vector. So to represent a vector, we are also going to go about this a little bit later. This would be a vector. An arrow is represented by a vector. Suppose, let's say this A is the initial point. Okay, so it's the initial point, and B here is the final point. All clear, right? So if you have to represent a vector that goes from A to B, where the magnitude is the length AB and the direction is the orientation from this initial to final vector, it would be represented as AB vector. So this is the representation. And if you want to know what is the magnitude in this case, I have already told you it's the length of AB, right? And the direction in this case, the direction will be the orientation of terminal point from initial point. So it will be from A to B. So from initial point to final point. Okay, so now let's talk about what is sense. So what is sense? So we gotta talk about that. So let's move on. So let's say there is a line. Um, so I have this line. Let's make it dotted. You don't have to make it dotted, but I will make it dotted. So what is sense? Let's make a definition for sense. So sense, to understand it, it's the infinite line. So it's a line going to infinity on both direction that carries the given segment the given segment the given segment of vector. So what does this mean? So when we are talking about this, so when okay, so let us continue. So when we talk about sense, we are talking about the infinite line that carries the given segment of a vector, which means it just gives you something about the vector that is important. So as direction is important, then it's give you that segment. So now let's look at a few points. So if we look at just a point, so let's just draw a coordinate system. Let's say this is a coordinate system where this would be y, this would be the x-axis, this would be the origin, and this would be the z-axis. Don't worry about the orientation right now. And we had to plot a point. Suppose this point is P and its coordinates is x, y, and z. So in this case, you would have to say that the coordinates of P, is going to be x, y, and z. So this is about coordinates. But if we were talking about vectors over here, so let me draw another one. And but if we were talking about vectors, so let's make a vector. So vector would be represented by an arrowhead, right? This, and let's say the vector goes from the origin to the point known as pxyz. So that's the coordinate. Then we would have to say that the position vector of p, which is also represented as op with a vector symbol, would be x, y, and z. So even though the representation is same, the meaning is different. In this case, we are talking about the coordinate of p, whereas in this case, we are talking about the position vector. So also you can represent this in terms of unit vectors. So before going to unit vectors, let's just tell what they are. This will be y, z, x. So unit vector is basically a vector that goes a unit in perpendicular directions. So let's say this vector in y-axis, the vector in y-axis would be j vector, and its coordinates or its vector will be 0, 1, 0. So this is not coordinates, it's the vector. And let's take another vector in z direction, which will be known as k. You can write them as k vector or k cap. So any unit vector can be written either as a cap over it or a arrowhead over it. So this will be 0, 0, 1, and for this would, for x direction, the unit vector is known as I cap or I with the arrowhead. So this will be 1, 0, 0. So we have the unit vectors now. So instead of representing as x, y, and z, you can also represent them as x I cap plus y z cap plus z zk cap. So that would be what we need. So now let's move on to vector representation. So how do you represent a vector? So vector representation. So vector representation can be done by coordinates and position vectors. So it can also be done by coordinates. So you might be thinking, how can it be done by coordinates or position vector? So coordinates and position vector are responsible. Okay, so for position vector and coordinates, we talked about position vector just now, but suppose we had two coordinates x1, y1, z1, and y2, x2, sorry, x2, y2, z2. Then let's say um, av vector, it's gonna be written as ov vector. This is the position vector from origin to b minus oa vector, position vector of a. This will be x2 minus x1 comma y2 minus y1 comma z2 comma z1. So this is a little bit advanced course, so I'm not going to go into detail for most of these things, because most of the things you must have already learned in previous classes or previous sessions. Okay, so now let's talk about triangle law. So vectors can be added by triangle law if you have only two vectors. So let's just draw a triangle. So let's draw this triangle. This can be any triangle. In this case, this is a equilateral triangle, but it does not have to be an equilateral triangle. So let's just say we have a triangle, let's say a b c. Okay, and this is ab vector, this is bc vector, and we need to find the resultant of ab and bc. So in this case, the resultant will be this ac. So the third side will be the resultant. So this is the condition for conformity of addition. So this confirms that it is about addition. So now, so the vector ac, which is known as the resultant, will be ab vector plus ac vector, where this is the resultant. Resultant is basically what you would get if you did both of them. You replace both the vectors with another vectors that would satisfy all conditions. Also, let's talk about parallel displacement. So when we are talking about vectors, and we are not talking about rotation in this case, we are just talking about vectors, you can move the vectors. So for example, let's say we had this vector, you can always move this vector by shifting it parallelly. So this is parallelly, and both this, so I'm going to copy and paste since this length must be equal and it goes here. So now I can move this vector to I can move this vector. So this is parallel shifting, which can be done with vectors. Okay, it's not the exact, but you understand what I'm saying. So let's also, to make this much more clear, let's make this dotted, since you know that we move this and the original place of the vector has been shifted to this place. This is called parallel displacement. So parallel displacement or parallel shifting, you can call it many words. So now let's move on to parallelogram law. So if you have learned this law before, you must know that this law is very similar to triangle law and is pretty much equivalent, right? So let's draw a parallelogram. Let's draw a parallelogram pretty quickly. Let's see how quickly I can draw this side. So the parallel sides, I'm sorry, we have to have parallel sides, right? And we need this line to connect. We're gonna suppose this is connected because it doesn't seem to want to cooperate with me, and I don't have the patience to do it very accurately. Okay, so now let's also draw the diagonal like this. So let's call this parallelogram A, B, C, D, and let's say AD is a vector and AB is a vector. Then the resultant would be AC, and also this AD vector will be equal to BC vector since we parallel shifted this. So that's why we talked about parallel displacement. So we talk about here these two vectors must be co-initial such that the diagonals will be the resultant. And if you have to write this will be AC equals AD vector plus AB vector. So since I want to show that this is equivalent to this, we know that this is equivalent. So equivalent to triangle law. So even if you did it by triangle law, this would be with BC side and AB side would be your sum, where AD is equal to BC, so that would still make sense. And so that's it. I don't think I need to go much deeper in this. So now let's talk about subtraction of vector. Subtraction of vector. So when we do vector subtraction, it's basically addition of vector, but we are putting a negative sign on a vector. So it's addition of a negative vector, you can call it like that. So let's say there is AB vector minus AC vector, it would give you CB vector. Okay, so this is an example. You can take this and you can modify into this. So we basically did this. I hope this makes sense. This should, since you are learning these, you have already learned this. So let's talk about a few more things. That's about the general concepts. So let's say there is 2 points, okay, x1, y1, z1, and x2, y2, z2. Then a few things that you must know is the direction ratios. So the direction ratios will be x2 minus x1, y2 minus y1, and z2 minus z1, right? So this will be the direction ratio, and the magnitude of the vector. So that it's a magnitude, you need to put this modulus sign on both sides. So if you do this, the answer will be square root of x2 minus x1 whole square plus y2 minus y1 whole square, and you can probably tell it's going to be z2 minus z1 whole square. So this is the formula for finding the magnitude when you have the points, the initial point and the final point. And finally, the direction cosine. The direction cosine is very similar to direction ratios, but what you do is you go x2 minus x1 divided by the magnitude. You can also write the magnitude just like this. If you write it like this or like this, it's equivalent. So you can put the modulus sign and do it that way, or you can remove the vector sign, the arrowhead, and that will give you the same result. So these are the direction cosines, and I think you should have already learned this before, so I'm not going into depth in this, since this is not even, we are not even starting the main new things in this chapter. So now let's go to another topic that you must have learned pretty early on, which is known as scalar or dot product. So it's scalar product or dot product. So let's say we had two vectors, then we had to do something. So let's say this is a vector and this is another vector, and let's take a line that is perpendicular to this. Now let's say this is O, this angle between these two vectors it's theta, this is v vector and this vector is a vector. This perpendicular point has dropped to M. So let's move this a vector to the side. Okay, let's move this a vector here, M, and this point is B and this point is A. So position vector of A will be A vector and position vector of B will be B vector. So in this case, we must know that the dot product, which is written as A dot B or B dot A, it will be AB cos theta, where A and B are the magnitudes respectively. So you can also write this as this, which is equivalent. And as you can see, there is no multiplication sign, because this is equivalent to this, which is equivalent to this. So this is the dot product. So scalar dot product is equivalent to this, and we will also learn that the cross product, which we will learn later, is also equivalent. So we don't need to write it, and if you write it, it just makes it more confusing. That's why we are not going to write it. Okay, so this is the dot product, and this is like the first thing that is important in our course. Now, so let's just look at a few cases. So let's say vector A is parallel to vector B. So what would be in that case? We can say that A dot B, so if it's parallel, it's going to be either 0 degrees or 180 degrees, right? So that would mean either it's going to be AB, right, or minus AB. So it's going to be AB when they are in same direction, and it's going to be minus AB when they are in opposite direction. And when I'm talking about the direction, we are talking about the vectors, the original vectors. Okay, so let's say A vector is perpendicular to B vector, right? So in this case, the value of theta would be 90 degrees, which would mean A dot B vector would be 0. And this is also another thing that you must remember, or you can also use this formula and to get to here. This parallel case is not that important, whereas this perpendicular case is much more important. So now we learned about scalar product, but what does this mean? So to understand its meaning, we're going to have to look to geometrical meaning and physical meaning. So physical meaning in equations in physics or in stuff like that, whereas geometrical meaning in figure. So from figure. So this means we know that A dot B is gonna be AB cos theta, and we know that B cos theta, you can see over here, B cos theta is just the projection. So this will be A times projection of B vector on A, this value, and A is just the length of A. So this is the geometrical meaning, which you should have already learned as well. And the physical meaning is that we can do A dot B, right, equals to AB cos theta, and we can write this as B cos theta A, which is basically work done. So this B cos theta is the scalar component of force B in the direction of A, so where B and A are vectors, and A would be the displacement through the distance A. So you can so this would be, I think, much more easier to understand if we did it like this. it's going to be force times displacement, or FD cos theta. So basically this portion is equivalent to that portion. So this is the physical meaning of scalar product. So now let's move on to calculation of dot product if we have the components. So if you have to do it by component wise and we don't have the magnitude of a or b, you would, let's say, a vector is going to be a1 I cap plus a2 j cap plus a3 k cap, and you can extend this to any dimensions you want, and this will be b1 I cap plus b2 j cap plus b3 k cap. So what would you do? You would have to multiply each terms, and you must know few things. Where we talked about the perpendicular case, so when two vectors are perpendicular they will be 0, and in this case it will be perpendicular if I vector multiplies with j or k, and similarly so we know that it's not gonna be 0 only when the same vectors multiply. That's why the answer you get will be b1 this, 2 b2, a3 b3. So this is the component wise formula. Also, sometimes you might get a question to find the angle between the two vectors when you are given the two vectors. In that case you use this formula. This formula is basically from the original definition, we just modified a bit, but so this is the formula. So now we talked about the dot product. So this dot product gives you a scalar value. But what about a vector product? So a vector product is also known as a cross product, right? And this gives you a result of a vector. So let's just make two vectors. Let's say there is one vector that goes like this, another vector that goes like this, and let's say another vector that is perpendicular to both the vectors. So listen what I'm saying. It is, this vector is perpendicular to both the vectors. So this vector is perpendicular, right? And let's call this vector n cap. So this n cap is going to be a unit vector, but we are not going to talk about it right now. So let's say this is O, this is B, this is A, and let's say the angle theta is taken from A to B, right? So theta. Since we are going to get a vector, this angle matters from which direction you are taking it. So let's say this is B vector, this is A vector, and the cross product goes like this. So A vector cross B vector, so A cross B is going to be AB sine theta. So everything normal, it was cos, now it is sine, but there will be this n cap, and this n cap is a unit vector. So we talked about unit vectors, right? So unit vectors perpendicular to the plane of A vector and B vector, right? So this is what we need to know. So now also the magnitude of n, since it's a unit vector, is going to be 1, and this formula is also something that you need to know. So let's say you need to find the angle in this case, and we already know that cos theta formula, so it's going to be similar. So it's going to be sine theta is equals to magnitude of A cross B divided by AB. So in this case magnitude comes up since we need to multiply the quantities without getting a direction. We don't need the direction when we are calculating sine theta. So that's it. Now let's go on to the geometrical meaning. So what does it mean geometrically? So let's say we took the magnitude of A cross B, then the unit vector would disappear, which is AB sine theta. So now let's look at a picture and think about it. Okay, so let's draw a parallelogram. I'm not gonna be that careful in drawing this. I'm just gonna do it pretty much freehand. So it might not be a perfect parallelogram, but let's just try to make it one. Close enough, right? Okay, so this is a parallelogram, let's say, and let's say this is O, this is A, C, B, let's say this is vector B, this is vector A, and this is the angle of theta. So now let's talk about what is b sine theta. So b sine theta would be this length, right? This length of this perpendicular drop would be b sine theta. So let's see, b sine theta, we have that, and we have the magnitude of a. So if you look at this, this just gives you the area of the parallelogram, the area of the parallelogram. So this is the geometrical meaning, and so this is the geometrical meaning. Also, sometimes you are given component, so you have to solve a cross b. When you are given a component, then you do it like this, and this can also be extended to as many dimensions as you want, but in this course we are mostly gonna be in 3 dimensions, so I'm giving you formulas mostly based on 3 dimensions unless it's necessary. So you have this, but it still doesn't tell you what to do. I don't know what this means, but it will make sense if I do this. If I put this symbol, it means I need to find the determinant of this matrix, and this formula is also pretty important. It's not as intuitive as the dot product, even though it is intuitive, but it's not that intuitive. Okay, now let's go on to the physical meaning as well. So what does it mean physically? So it means torque. Why? Let's see. Let's say tau. Tau is a vector, which is a torque, and let's say r cross f. You can substitute these values and you can see that this is a torque. So what does it mean by a torque? So a physical significance of a torque. Let's suppose you have a tap, right? And you rotate this tap, okay? So when you rotate this tap, water starts flowing out, right? So this is the significance of torque. So this is what the physical meaning is. You can write it as torque, it's the simple version, or you can give this tap example, which is also pretty simple. So now we are getting to the main point of this lecture. So in this lecture, this is the main point that I'm trying to show, and which is scalar triple product or box product. Scalar triple product, or you can also call this the box product. So you might be confused why it is called box product and why it is called something scalar triple product. So this is the first new thing we are going to talk about, so that's why I'm going to go in a little bit of depth. So this triple scalar product is represented by a vector dot b cross c, and this will be represented at this. So since it is represented like this is a box, right? So it's called box product, and the result of this is a scalar, hence it's called scalar triple product. And if you are given the components, you calculate it like this. And this is also pretty easy to understand, since we already talked about the cross product as well as the dot product. So if you just think about it, so I'm going to leave this as an exercise to you. This will be the result, and this is another formula that you must know. Okay, so now let's talk about the geometrical meaning. So what does it mean geometrically? So it means, I'm not gonna go in too depth about this, so let's believe what I say, right? It's gonna be the volume of a parallel pipe whose initial ages are A, B, and C. So that might not make a lot of sense right now, so I will try to make it much more sensible. So first of all, let me make the figure. Let's say this is vector A, this is vector C, this is vector B. Then the result will be volume of parallelo pipe, I don't know how to pronounce this that well, whose initial edges initial edges, or you can also call this coterminous edges, are A, B, and C, and initial can be replaced by this word, which is coterminous. Okay, so this is the geometrical meaning. It gives you the volume. So okay, that makes sense, right? So now let's talk about the properties. So since this is a new thing, we need to talk about the properties and how does this work. So properties work. The first property I'm going to talk about is that you can write it like this. We know the box product is this, right? So this will be equal if you just rotate this cyclically. So we are just rotating this, and all of these will be equal. Pretty neat, right? So this is the first property, and a second property is if, let's say, ABC box is 0, then this means all of them are coplanar, and this is one property that you must know, since multiple questions come up from this property. And finally, this is the way. So um, now we talked about scalar triple product, and now let's talk about vector triple product. Since in vector multiplication of two vectors, you can get a scalar and a vector result. Similarly, in this case also, in triple product, you can also get a scalar and a vector product. So the vector triple product. So this does not have a name like box product. So um, you can do this in two ways. Okay, so vector triple product can be done in two ways, right? um, so we just talked about the scalar triple product. Now we talked about the vector triple product, and there are two ways of doing this. So first way you can do this is um, A cross B cross C is equals to A dot C, and I don't recommend that you remember this formula because it's much more easier if you just do the calculations, because it's easier. So now let's talk about the scalar and vector product when we multiply four vectors. So this is it. This is the scalar triple vector triple product. This result would be a vector. Now let's talk about if we had four vectors. Okay, so let's say if we had four vectors, you can do two ways. So let's say this is one. You can put a dot over here, or you can put a cross over here. So there will be a dot, or you can go like this: A cross B cross C cross D. So for this case, the formula is actually pretty simple, and I would recommend that you know this formula because it's quite helpful when doing calculations, since it is a pretty small determinant as well, right? And the result of this is actually a scalar product. So this is scalar product when we are doing multiplication of four vectors, and this is a formula that I would recommend you to learn, whereas for this I would just recommend that you do the calculations rather than using the formula, because the formula is also pretty complex. So you need to take the box product, then multiply it by another vector, then again take the box product. So at this point, if you have the values, it's going to be easier to just do the calculation that rather than using the formula. But I'm still telling you the formula because who knows, you might need it some time. So this is the vector product, and these formulas are also pretty important, but not that important as the triple products. So this is the first part done. So that was the first points, the everything that we learned. I hope you have noted down, since you would kind of need it if you're learning this. So this was the review of scalar and vector products, scalar and vector triple products, scalar and vector product of four vectors. In the next class, we are going to learn about vector differentiation and integration, their geometrical meaning, and velocity and acceleration.